related to the cardiovascular. This is blood flow measurement. So here, what is the difference between the blood pressure measurement and the blood flow measurement is, blood pressure is the force exerted. Here, blood flow measurement, it is more on the volume. How much? What is the quantity of blood coming out of the heart in a time gap, in a time interval? So that's the blood flow measurement. So the blood flow measurement is also a very important measurement in the case of cardiovascular functions. So that gives you an idea about how the overall pumping activity of the heart. Is it pumping efficiently, or is it pumping the sufficient blood output? Is it, are the body is getting sufficient blood supply? That can be identified, or that can be studied with the help of this blood flow measurement. It is also an important physiological phenomenon. The rate at which blood flows through the blood vessel within our body can be measured using blood flow meter. So here the rate means what is the volume per unit time. So what is the quantity of blood coming out at a time interval? That's the blood flow measurement. So this is a picture where the reason for the reduction in the blood flow. If you see in the first figure, the arteries are very clear, there is no obstruction, so the blood flow will be normal. But in the case of the second one, there is a clot, there is a obstruction in the vessel, and due to that there will be a drop in the blood flow. So the blood flow will be reduced and the velocity will be dropping. So that can be identified. So if you see, say now, for finding out the problem in the vein or in the artery, there is any blockage, there are different procedures like imaging procedures are there. But before we perform that, we can have a blood flow measurement, blood flow check, and if the blood flow check tells you some deviation, then we can go for the confirmatory kind of diagnostic procedures like imaging procedures, where it can be exactly find out what is the problem in the vessel due to what there is a drop in the blood flow that can be identified. Actually, the blood flow measurement, there is invasive and non-invasive procedures, and mostly there are invasive methods. The non-invasive methods are it's kind of normal strain gauge measurement, or you can go for an ultrasound method. We'll come to that later. Before that, the non-invasive types, we can talk about an electromagnetic flow meter. But this electromagnetic flow meter, when you're talking about the electromagnetic flow meter, you can't say it's a completely non-invasive, because these electromagnetic flow meters are used for industrial flow measurements, where we cannot afford to disturb the flow of the fluid. So here also the same, which is applicable for in our case. Here we can't afford to disturb the blood flow. So that's why we can go for this electromagnetic flow meter. But the problem is, we need to have the access of the artery where the blood is flowing. So it is not a completely non-invasive method, and mostly this electromagnetic flow meter is suitable during some surgical procedures, and it directly gives you the exact flow measurement. The electromagnetic flow meter, it is working under the principle of Faraday's law. Faraday's law says that when a magnetic field is applied on a moving conductor, there will be a EMF produced. So I have said 3 points: magnetic field, moving conductor, EMF. Now all these three will be perpendicular to each other. So it is so these three parameters: magnetic field, velocity of the moving conductor, and the EMF induced. So the three things will be perpendicular to each other. Now this three parameters are derived, it's like The EMF induced is given by UBL. So here U is the velocity, B is the magnetic field, and L is the diameter of the conductor, length of the conductor where the magnetic field is acting. So for a uniform B, that is uniform magnetic field, for a uniform velocity profile U, and induced EMF E is given by BLU, where of course E is equal to electromagnetic field induced by the magnetic field in the moving conductor, and U is the velocity, and cross-sectional area is A. Now from this, the induced EMF, see, ultimately the summary is the induced EMF E is proportional to the velocity. Now velocity is the flow rate, of course. The velocity means how fast the blood is flowing. So from the velocity profile we can find out the flow rate. So ultimately we are trying, using this electromagnetic flow meter, we are trying to find out the velocity of the blood profile. So from the induced EMF E, which is proportional to the velocity and magnetic field density and the length of the conductor, if you make the magnetic flux and the length as constant, so E is directly proportional to V, and once you measure the EMF induced in the conductor, then we can find out the velocity. So that's the electromagnetic flow meter. There are so many different variations in the electromagnetic flow meter when it is used in blood flow measurements. So in the electromagnetic flow meter probe, it will be looking exactly like this. So here the vessel will be kept here. The blood vessel will be kept here, and it will be directly touching the electrodes. These two electrodes are used to capture the induced EMF, and you have the magnet, the permanent magnet, and it's an electromagnet, and the electromagnets are magnetized with the coil, and it is captured. So the vessel will be running like this. So this the artery which carries the blood, which is perpendicular to the magnetic field and also to the electrodes. So the EMF will be induced on the electrodes. So as I told you in the previous slide, the EMF induced is proportional to the velocity of the blood which is flowing through the moving conductor. I mean, here the blood is the moving conductor. Now the problem with this electromagnetic flow meter is, as I told you, there are this is the practical electromagnetic flow meter probes, which is shown in this figure. So there are different types of electromagnetic flow meter. There is a permanent magnet electromagnetic flow meter, then DC excitation electromagnet, AC excitation. So permanent magnet, of course, it's not a suitable method for blood pressure measurement, because the size matters. The size is very huge in case of a permanent magnet. So we normally go for electromagnets. So electromagnets is one which behave like a magnet when it is electrified. When you're supplying an electric current, it becomes a magnet. So it's a coil. It's a coil where it will perform as a magnet when the supply is on. So that's an electromagnet. And how we excite the electromagnet, what kind of current we give for the electromagnet. Based on that, we can classify this electromagnetic flow meter into two: a DC electromagnet, AC electromagnet. So in the DC electromagnet, there is a process called polarization, and due to this polarization, again, so the polarization will affect the induced EMF, that will disturb the induced EMF, and due to that, the electrodes which is used to capture the EMF, induced EMF, will get polarized. So again, DC excitation is not a suitable method for blood flow measurement. So only option is AC excitation. So what kind of current you are giving to the electromagnet, that's called AC excitation, alternating current. So in the alternating current, what happens when you are giving an alternating current? The sine wave, again, what kind of alternating current? Alternating current means it's a pulsative. So what kind of current you are giving, whether you are giving a sine wave or a square wave or a different waves. I mean, there are trapezoidal waves and so many different waves. Now the basic wave is a sine wave. When you give a sine wave, what will happen? We'll see. Now the sine wave is used to excite the electromagnet. Now we are giving a sine wave, and the electromagnet is getting excited, and it is giving a magnetic field to the artery which is carrying the blood, and of course there is a conductor electrode which is capturing the EMF. Now the electrode which is capturing the EMF, that's the induced EMF, that is the signal of interest. Now, due to this sine wave, when you are giving a sine wave and there is a coil motion, there will be a transformer effect. So what is the transformer? The coil, the electromagnet will act as a primary coil, and the blood flow will act as a coil. So it will become a secondary coil. So there will be a transformer effect. So this transformer effect will induce an additional voltage, that is kind of a noise signal, and that will superimpose on the induced EMF. When that is superinduced and induced EMF, and interestingly, the transformer voltage is higher than the signal of interest. The amplitude wise is higher than the signal of interest, and signal of interest, that is the induced EMF, due to the velocity profile, is less than the transformer voltage. So because of that, removing the noise and getting the signal of interest from the overlapped noise signal, we need to have high-end filters, and the total mechanism of measurement technique becomes complicated. So then what is the solution for that? So instead of a sine wave, if you excite the electromagnet with a square wave. So what happens when you excite the electromagnet with a square wave? So when you excite the electromagnet with the square wave, so this is the transformer voltage. So in the first waveform, you can see this is the signal of interest, and there is a transformer voltage which is a 90-degree phase shift, and there is higher than that. When you give a square wave, actually this is the square wave, and the first one is the input. The first one is the input to the electromagnet, and this is the signal we capture. Now if you see the signal which you are capturing, there is a difference. This is the input which is given to the electromagnet, and this is the output which you are getting from the electrode, that is the induced EMF output. Now in the induced EMF, you see there is a spike. So this spike or the transformer, due to the transformer effect. Now you see here how big the transformer voltage. It is, of course, it is another. It's look like another signal, totally different from the signal of interest. But here the spikes are very less. It's negligible, and you are getting actual induced EMF overlap. The spikes are getting overlapped in that. Now the removing the spikes becomes a very simple process. You can easily remove that spikes, and we can get actual signal of interest. So the square wave excitation, in that way, it gives you a good output. Then there is a variation, that's a trapezoidal waveform. So trapezoidal waveform, still the spikes are reduced even lesser. So this is how we can measure blood flow using an electromagnetic flow meter. So in this session, I have given you some information about the blood pressure measurement and blood flow measurement. These two measurements are essential measurements for identifying the problems associated with the heart. So whether the heart is functioning properly, whether it is supplying the required blood in a sufficient pressure with a sufficient velocity, that can be identified or measured using these two methods. And we have discussed the complete method, procedures, measurements, the positive and negatives of that methods, and the variation in those methods. Everything we have discussed in that. So I conclude with that. In my next session, I'll be discussing about another method, another technique, which is also an indicative tool for heart function, that is cardiac output. So thank you very much for listening my lecture.